Hello everyone. This is section 14.6, Directional Derivatives. So we start with the definition. Here's the notation. This is read as the directional derivative of the function f at the point x sub 0, y sub 0 in the direction of u. And that's a unit vector. So the unit vector given by u1i plus u2j. So the interpretation of what this means is basically the slope of the surface in the direction of u at that point x sub 0, y sub 0, and z sub 0. For example, if we consider, say, a little figure here. So you have our x, or y, and our z axes, and we have, let's say, a surface, some surface, and this surface is going to be z equals the function of x and y. That's our surface, and we have some point in the xy plane. So maybe 1 in the x, 2 in the y, or 1 in the x, 1 in the y, whatever it is. We'll just denote that as x sub 0, y sub 0. And the idea is that you have a line which represents the unit vector. So if I take a line through the point in the xy plane, let's say I call this L, and here would be my unit vector. There's a little one unit, call it U, and that would slice through the graph of the surface, let's say along something like this maybe. Okay, and so then projecting this point right onto the surface, that would be the point x sub 0, y sub 0, z sub 0. And you could find z, of course, given x and y just by plugging it into whatever the function is. So then the idea is that it's essentially the slope, the directional derivative would be the slope along that. So this is our slope. Okay, so that's the concept of what the directional derivative actually means. So here's how we find them. If we have a unit vector, then here's a formula for the directional derivative of the function in the direction u, and it's just the partial of f with respect to x evaluated at the point times u1, and then plus the partial of y evaluated at that point times u2. And then we can extend that to further to a function of 3 variables, as we did here. So one of the important things to remember is you need a unit vector, and we'll see that in this reinforced in our second example. But in the first example, we're given the unit vector, and we're given the function, so we just need some partials with respect to x and with respect to y, and we're given the point as well. So you find the partial with respect to x. That's going to be 2x minus 5y. Remember, finding the partial with respect to x, y is held as a constant, so the derivative of x squared is just 2x. Y is a constant, derivative of negative 5x is negative 5, so tag along the y. And then if y is a constant, derivative of 3y squared is 0. Similarly, we'll find f sub y. Derivative of x squared will be 2x. Here x is a constant, because x is a constant. Here x is a constant, or negative 5y, negative 5. So negative 5 when the x tags along, and then the derivative of 3y squared is 6y. So then it's advantageous at this point to actually evaluate before we substitute into our formula. We'll evaluate the partials at the given point. So f sub x at 3, negative 1 would be 2 times 3 minus 5 times negative 1. Or 6 plus 5 or 11. And f sub y at the point 3, negative 1 is going to be negative 5 times 3 plus 6 times 1. So f sub y at 3, negative 1, negative 15 plus 6 or negative 9. And so then we're going to substitute into our, made a careless mistake there. Y was negative 1, so 6 times negative 1 would make this a negative 6, and therefore a negative 21. So that was a negative 1, making that negative 6, so negative 21. Okay, so now we're ready to substitute. Notice that here we have u1i plus u2j. So into our formula, okay, we could write at 3, negative 1 is going to be f sub x. I'll write it formally here. At 3, negative 1 times u1 plus f sub y at 3, negative 1 times u2. So we have 11 times radical 2 over 2 plus u1, and then plus a negative 21 times radical 2 over 2 is u2 as well. So 11 radical 2 over 2 minus 21 radical 2 over 2, giving us negative 10 radical 2 over 2, or minus 5 radical 2. So that represents the slope in that direction. Okay, but as a note here, if the unit vector is not given, we have to find the unit vector first. So here it's given as a, and so for a, the unit vector is going to be the vector a divided by its magnitude. So recall that. So first we'll have I plus 2j minus 3k over magnitude, recall, square root of the sum of the squares. So 1 squared plus 2 squared plus a negative 3 squared. And so we get I plus 2j minus 3k over square root of, see, that's 1 plus 4 is 5 plus 9 is 14. So 1 over square root of 14i plus 2 over square root of 14j, and then minus 3 over square root of 14 times k. So those are the u1, u2, and u3 respectively, coefficients of the ij's, k's. Okay, so now we could start with the partials. We're going to have 3 of them in this case. Partial with respect to x will be y cubed z squared, because the derivative of x is 1 and those are held as constants. Partial with respect to y, 3y squared is the derivative of y, x and z squared tag along as constants, so 3x y squared z squared, and then the partial with respect to z is going to be the derivative of z squared is 2z, x and y tag along, so 2x y cubed z. And I spread these out a little bit because I'm going to evaluate them first. I think it's up to you. You could do it any way you like. Excuse me. But I think that's most efficient, like we did in the last example. Okay, so now evaluating each of these at the given point. F sub x of 2, -1, 4 would be -1 cubed 4 squared. So that would be -16. F sub y at that point, 2, -1, 4, it's going to be 3 times 2 times -1 squared times 4 squared. And let's see, that's 16 times 2 is 32 times 3 is 96, and it's positive because -1 squared is positive 1. And finally f sub z at that point, 2, -1, 4, 2 times 2 times -1 cubed times 4 . So that would be 4, 8, 16, it's going to be negative. Okay, so then the directional derivative and the direction of u of the function f at the point 2, -1, 4. If you want to write down the formula, or if you just want to jump right in and make the substitutions of the partials times the u1, u2, and u3 respectively. I'll show it writing down the formula. It'll take a minute to do that. So we have, it's going to be f sub x at 2, -1, 4 times u1 plus f sub y at 2, -1, 4 times u2, and then plus f sub z at 2, -1, 4 times u3. Remember, up here, this is the u1i plus u2j plus u3k. Okay, so just plug it in now. What we have, -16 for f sub x at that point. u1, 1 over square root of 14, plus f sub y was 96, times 2 over the square root of 14. Again, back up here for u2. And here's u3. F sub z first, -16. And u3 was 3 over the square root of 14. Okay, so that gives us So negative 16 over the square root of 14 plus, that'd be 192 over the square root of 14, and then minus 48 over the square root of 14, which combines to give us, let's see, the 48, 58, 64, minus the 192. Oops, I made a mistake here, sorry. This was a negative 3 radical over radical 14 for U3. So make sure you slide that negative in there, that makes that positive, okay? And so now we get 240 minus 16 is 224 over the square root of 14. And you could rationalize this and reduce it if you like, but I'm going to be satisfied at that point. Okay, so I think we'll stop right there for this part of the video. Probably going to be a couple more parts because this is section has a little bit of substance. So this was part 1 for section 14.6, directional derivatives, and we'll see in a few minutes for part 2.